Apologies, there's a lot of stuff here. Here's that 40,000 base pair piece of DNA, and then we broke it down into different sections, and we redesigned all the sections to make it more understandable to us. So for example, the sequence that we were just looking at, 2.8 and 3, is depicted right here, and you can see we pulled them apart. And then we did that for everything across the whole genome, making hundreds of changes at the same time. And then we built that piece of DNA, and we put it back into cells to see what it would do. And the big result for us was that after making about 600 changes at once, the program was still viable. So on the left, what you're looking at is a Petri dish. It's a 10-centimeter plastic dish. It's filled with Jell-O. And this is the natural virus. This opaque white background is bacteria that are scattering light. And then the circle here, the dark circle, is where the virus is growing and replicating and propagating. So you can think of it this way. If you're up in a satellite or the space station and you look down at a forest and you've parachuted a lumberjack into the forest, and every time the lumberjack cuts a tree down, you get 10 more lumberjacks and they keep cutting down trees. That's what these circles are. So depending on how good your lumberjacks are or how good your virus is, that will define the size of the circle, how quickly it grows. And you can see the natural virus is really, really good at clearing out holes in bacterial forests, whereas our engineered virus makes much smaller holes. So it's not as good. It's not as fit. It doesn't grow as fast. It's about 40% lower fitness. So the question to us was, is this a good trade-off? Are we willing to give up 40% reproductive fitness for much, much more understandability? In the wild, this thing would never survive, but in our laboratory, this has a lot of features that we like.